Now we just continue with the next section, 2.10, addressing. This part we already talked in last class. I just want to mention again, branch of equal, right? And one important section in branch of equal assembly language is the label of the instruction we want to branch into if the condition of the branch satisfied. But I mentioned, although that label represented as an ASCII value, but the actual assembler will translate this ASCII value into a 16-bit, which associated with the memory address of the instruction with this label. Again, because all this sampler want to translate or can translate is into 16-bit, which is different from the number of bits of the memory address, because now bits of memory address is 32 bits. However, here I only has 16 bits. So in order to address that issue, basically in this 16 bits, I will not put the absolute memory address of the instruction with this label. Instead, I will put the relative address of the instruction with this label compared with some reference address. And that reference address is PC plus 4. Okay, so basically PC plus 4 plus something related to this segment will be equal to the memory address of the instruction with this label. So what is the implementation? Implementation is appendix to zeros at the end. In other words, in hardware wise, I will take this segment, I will extend two zeros at the end, and then I will do some extension in the front, which is shown here, right? I take the immediate field, do two zeros at the end, and do some extension. After that, I will get a 32-bit value, and then I will using this 32-bit value to implement addition with PC plus 4. In other words, the target address is equal to PC plus 4 plus immediate field times 4. Why is times 4? The reason is I do two zeros extension at the end, which equivalent to do the shift left logic for this immediate field value. And then we said, as long as you shift something to the left by n bits, is equivalent to implement multiplication, which is to multiply this value with 2 2's at the end. So one more time, you do two zeros at the end. Let me just repeat here. Extend two zeros at the end is equivalent to implement shift left logic for the immediate field, which is equivalent to the immediate field times 2 n. Here, because here n is 2, right? N is 2 bits. Here 2 2 2. Okay. Say one more time. You extend two zeros at the end, equivalent to implement shift left logic for the immediate field with 2 bits, where you basically you shift this immediate field to the left by 2 bits, right? And then which is the equivalent to do the immediate field times 2 2 2. Okay, I hope it is clear. And then just here give an example. Okay, assume you have a program counter is 50000, and then the branch address basically your the immediate field you have that value is 500. So I want to ask the memory address of the instruction with that certain label, which is equal to, basically I tell you the immediate field, I tell you the program counter, I want you to tell me the target address, basically it's the memory address of the instruction with the label, which is equal to the PC plus 4 plus immediate field times 4. PC is what? It's this one, right? It's 50,000. And what is the immediate field value? Is 500. Therefore, you plug in, you will get your target address is as following. Hope it is clear. So one thing just to mention, so if here, so you can see the immediate field is only 16 bits, right? In other words, you have a very limited range you can jump into, okay? So that means, that's why I mentioned here, that means most branch target is actually near the original instruction, which is the instruction with the memory address of PC. The reason is because the maximum you can branch is 4 plus this value times 4. Okay, so this is all the the range you can branch to, right? So in other words, normally we know the branch and the jump both can transfer control, but the branch can only transfer control in some place nearby. Okay, so different from the conditional decision making, which is branch or branch vehicle, which is jump or transfer the control to the place nearby. The jump, this instruction is actually can branch or the transfer the control to a much further place. The reason is because this jump, right? The standard format is J, which is the notation of a jump with the label, and then this instruction we using J format. Basically, they have the operation code, and then all the other 26 bits will all use as the jump field, or is also you can consider as constant field. Say one more time, in the J format, you basically only have two fields. Okay, one is immediate field. Where is the here? Okay, so sorry, one is the operation code. You only have two J format. You only have two fields. One is operation code, another is a constant. Okay, so just make you can do some comparison. Immediate field basically have operation code, which is similar, share the same field with the J format, but has another two field, right? One is RS, one is RT. After that, you can have the immediate field, which is also contain constants. And then if R format, you even have more field, right? Will share the same segment with the first of three segments with R format and F format, and also you will have another two segment. Say one more time. R format you will share the first three segments same as the I format, and then you will have another two segment. Basically, it's operation code, RS, RT, and then the new one is RD, and RT, sorry, and then shift amount. Right, and then the last one will be the function code. Okay, so again, because of that, you have much larger, much more bits you can represent in for your memory address. Therefore, J format potentially can transfer the control into a much further place. So how basically you can see here is some information associated with the memory address of this label, how you really calculate your destination memory address, which is the memory address of the instruction with this label. So actually what I do is I will take this 26 bit, okay, also similar to the branch, I will do 20 extension to the end. After that, basically I will have totally 28 bits. Still have 4 bits need to fill in order to get 32 bits. This 4 bits actually is the first 4 bits of program counter. Say one more time. So basically, I will take this 26 bits, do 2 zeros at the end, and then I will have totally 28 bits. So I'm still missing 4 bits. So what I do is I take the first 4 bits of program counter and then put that 4 bits in the front. The reason is generally speaking, although jump you can transfer the control much further compared with branch, but generally speaking, it's still within the range which share the first 4 bits with the current instruction memory, which is the first 4 bits of your program counter. Okay, that's why you can see the hardware realization is take that constant field, do 2-0 extension to the first 4 bits of your program counter, and then that value will be the memory address, the target memory address. Okay. And here, this example, I think we already go through the most of them. The only thing we now to go through, we go through all the first 5 instructions in the tutorial in last class. The only thing we now to go through is the jump. We said we will go through that after we talk about jump in more detail. So here, let's go through. So basically, this one, in order to represent this jump loop into the assembly language, first I need to into the machine language. First thing I need to know is what the format I use. Right? You pause here, try to answer by yourself. Here I know the format I use is the J format. Right? J format basically is first 6-bit element and then continue with the 26 constant field. And the first 6-bit operation called field, it is easier, right? Basically, you just write the operation code correspond to this operation, and you don't have to remember because as long as have that, I will provide it in the table. That will be 2. Again, you definitely need to translate this decimal number 2 into a 6-bit of binary number. Okay, but the problem is here. What I will fill in this constant field. This one I will fill in is you recall we just mentioned, right? So basically will be the, just let me get a new one. So basically is the, I have the constant field, do 2-0 extension, right? And then to do the first 4 bits of PC, basically 31 bits to 28, right? So basically overall this will be my destination. What is my destination? Destination loop, right? Basically destination is 80,000, right? So basically what I mean is if I try to call this one as x, okay, so basically x times 2 to 2, y2 to 2. Again, because I do 2-0 at the extension at the end means I shift x to the left by 2 bits is equivalent to times x with 2 to 2. Okay, and then do the concatenate the first 4 bits of PC. So what is the first 4 bits of PC? If you convert this 80020, which is PC, into the binary number, the 32 binary number, you will see the first 4 bits will be 0. Therefore, all I try to do here actually is the 0 extension here 0 extension, because this one is a unsigned value, basically non-negative value. 0 extension means I do sign extension, means I do not change any value. In other words, actually just x times 2 to 2 is equal to my destination, which is 80,000. Okay, so in that way you can calculate x is equal to 20,000. That is why you can see you put the 20,000 here. All right, I hope it is clear. So another thing is just summarization, the different addressing mode we have learned until now. First addressing mode is an immediate addressing. Basically, the address information is carried within the immediate field in the I format. Another is a register addressing. Basically means is, for example, R format, you basically does not give the real value of for example, A plus B equal to C, right? You don't give the real value of A is in your assembly language. Instead, you give the address of the register. You find that value from the register. Basically, I gave you, for example, here is T0, right? You will find that the real A value from T0. That is called register addressing. Another is called the base addressing. For example, you implement load word store word, right? So basically, you only know the instruction in the I format instruction for load word store word that the immediate field only is offset. You need using that offset add with the base address, right? So that is called the base or displacement addressing. Only the offset plus the base address you will get the real and the destination, right? You want to load from, load from or store into. So another one is a PC relative addressing. That one is when we talk about branch equal, branch not equal, right? We said in the immediate field in your instruction, the only give you is relative address. Based is the one you will use to calculate the final target address. Basically, is this immediate field times 4 plus PC plus 4. That will be the real memory address you want to branch into, right? That is the PC relative addressing. The last one is pseudo addressing. That will associate is a jump. Right? We said in the constant field in your J format only has 26 bits. Even you do 2 zeros at the end, you only has 28 bits. You still leave 4 bits in the field in the beginning, and that 4 bits come from the first 4 bits of program counter, right? So that is called, basically what you do is you take the first 4 bits of program counter and concatenate with that 28 bits. So that is called the pseudo addressing. Okay, so now we basically finalize all the material in topic 2. We will continue to about topic 3, the arithmetic for computers. Before we talk about the detail about topic 3, we want to provide some tutorial for digital systems. I believe the student lecture already provided the information here, and that in other words, TA already provided the information here. I just want to go through some more.